Hi guys, welcome to physics lesson 4.04, mass versus weight. They are not the same thing, and up until now, your teachers may or may not have really talked about it, but for our class, we sure do need to know what the difference is. So in the past, you probably defined mass. In fact, even in chemistry, I think I defined mass for you as the amount of matter an object has. The actual definition of mass is an object's resistance to inertia. An object's resistance to inertia. So rather than talk about the amount of matter or the amount of atoms, we talk about mass, especially in physics, as the ability of an object to not undergo inertia or to resist inertia. And remember, we said that mass and inertia are directly proportional. They're directly proportional. In fact, in space, scales don't work, and we'll learn why in a bit. But in order to determine, it's important to keep track of an astronaut's mass. As they are outside the force of gravity, they tend to lose muscle, they tend to lose bone density, and some of those astronauts are up there for a year. So they will put them into what's called an inertial scale or an inertial balance. And I'm going to pause this and pull up a picture. Okay, so I went ahead and I pulled up a picture. I'm going to share my screen. This is an astronaut in an inertial balance. So they sit in this chair, they get locked in, and there's a spring or something that causes movement, and they push the astronaut, and then they let the chair rock back and forth. And the faster it rocks back and forth, the less inertia there is, so the less mass there is. And so that's how they have to keep track of an astronaut's mass in space. Well, the reason why scales won't work is that weight is the magnitude of the force of gravity on an object. Whoops. I was writing my next sentence there. Weight is the magnitude of gravity on an object. And we're looking at very different units here. So for mass, our SI unit is the kilogram. By the way, in the English system, you guys might think it's pound, but you would be incorrect about that. So the SI unit for a weight, we're talking about a force. So here we have the Newton. The English unit for weight is the pound. So I'm going to write this up here. I think that's confusing. Here's the kicker. You've been using pound and kilogram interchangeably for a large part of your scientific career, and you are looking at completely different things. The actual English system unit for mass is a slug. So a slug and a kilogram are the same thing. A Newton and a pound are the same thing. These are not the same thing. One's a unit of mass and one's a unit of force. Know that, so if these are both forces, we know that force, let's go to green, is mass times acceleration. So we use mass to find the force. What you're going to see me do from this point forward is for the force due to gravity, I'm going to put F sub W, and the W is weight. because I want to reinforce for you that we're talking about a force and that weight is a force. Mass is what it always is. Over here now, we're going to put acceleration due to gravity, AG. What you'll see in a lot of textbooks is this. You'll see weight equals mass times gravity. I'm not a fan of this because you begin to think that gravity is this 9.81, and we talked about this being 9.81 meters per second squared down. And I don't like the fact that students begin to believe that gravity is 9.81. It's just that. No, that's the acceleration due to gravity. If you want the force due to gravity or the weight, you have to multiply the acceleration due to gravity by the mass. They're very, again, details, but details matter. So let's run a sample problem. Let's go back to red. So if I have a rock that has a mass of 6.5 kilograms, what is the weight? Well, I have to take that 6.5 times 9.81 meters per second squared, which is this, and I come up with 64 newtons. Here is a tip for you. Watch your units. If you're reading a problem and you see weight, or you see newtons, you know you're talking about weight. You can't be talking about mass because mass is going to be in kilograms. Common questions are, if an astronaut has a mass of 100 kilograms, which is a really heavy astronaut, maybe he ought not be an astronaut, and he's on a planet that has acceleration that is half of Earth's, well, you know, what would his resulting weight be? Well, if the pull of gravity is half, this would be 4.9. So on Earth, it would be 100 times 9.81. He'd be 98.1 newtons on Earth. But on a planet with half the gravity, acceleration due to gravity, he'd be 49 newtons. So that's kind of a more common question. Another thing that we should talk about right now too is that when we're talking about Newton's laws, they apply to objects that are fixed to the Earth. So if or in relationship to the Earth, we have what are called reference frames. If we're observing something and we're accelerating as we're observing it, we're in a frame of reference, that an inertial reference frame that won't work. So we're assuming that the observer is standing, is fixed to the Earth, or is moving at a constant velocity. And the only acceleration that we're taking into account is the acceleration of the system we're analyzing. You could see if I'm accelerating at 2 meters per second and I'm studying something that's accelerating at 10 meters per second, my acceleration is going to affect the way that I observe that other system accelerating. So that's kind of an aside, but Newton's laws don't work for what are called non-inertial reference frames. And let me just throw that in the notes. Newton's laws only work for non-inertial, it's called a non-inertial reference. And it basically means the observer is not accelerating. Sometimes you'll see a random AP question about that. So I thought since this was a shorter video, this would be a good chance to kind of throw that in. All right, so that's all we have on mass versus weight. Thanks for watching. Have a good day.